Welcome to this session of Shadow the Scientist, monitoring volcanic eruptions in Hawaii, processing volcanic samples from the June 2024 Kīlauea eruption. My name is Jamika Marshall, and I am pleased to serve as the Shadow the Scientist coordinator. Shadow the Scientist is an initiative housed under the Creating Equity in STEAM, or CREST, umbrella of programs offered by a team at the University of California, Santa Cruz. We offer free virtual public experiential learning sessions several times a month featuring professionals from a variety of disciplines. Scan the QR code on the screen for more information and to register for upcoming sessions. In this session, we have the privilege of shadowing petrologist at the Hawaiian Volcano Observatory. The island of Hawaii is one of the most volcanically active places on Earth, with its most recent eruption occurring on June 3rd, 2024. This eruption took place in the southwest rift zone of Kīlauea, which had not erupted since 1974. There are a multitude of ways to monitor and research volcanic eruptions, such as seismicity, petrology, gas emissions, and surface deformation. Now, today, a team from the Hawaiian Volcano Observatory will demonstrate what a day in the life of a petrologist, that is, a scientist who studies how rocks form, looks like using the 2024 eruption as an example. They will take us through the process of collecting samples in the field, processing them in the lab, and then preparing them for geochemical analysis. This work offers a window into the magmatic plumbing system that is underlying Kīlauea and provides a better understanding of how and why volcanoes erupt. I'd like to now welcome Kendra Lin, a research geologist with the USGS Hawaiian Volcano Observatory, to get us started. Kendra, welcome.
Thank you, Jamika. We're just going to take one moment and get our slides shared.
While we're waiting for Kendra and her team to get us started, please feel free to post your questions and comments in the chat, and we will get to those questions towards the end of today's session. All right, Kendra, take it away.
Thank you so much. We're very excited to be here today to share with you some of the work we've been doing this summer. First, welcome to the Hawaiian Volcano Observatory. We are located in the Hawaiian Islands, which are here, sort of sitting lonely out in the middle of the Pacific. It's a nice Google Earth image that shows this classic example of intraplate volcanism. Now, the Hawaiian Volcano Observatory is actually just one of several within the U.S. Geological Survey's Volcano Science Center. So within our group, there are several observatories in Alaska, the Cascades, Yellowstone, and in California. And our partners in these other observatories often do work like the work we're about to show you today. The Hawaiian Volcano Observatory, or HVO, used to reside in a building that sat on Uvekahuna Bluff in Hawaii Volcanoes National Park, overlooking the summit caldera Kuluapele at Kīlauea. This is a photograph of Halema'uma'u crater with a lava lake nested inside. Now, this lava lake was active between 2008 and 2018, so about a decade. And this photo rather demonstrates quite well that the Hawaiian Volcano Observatory's job is to observe volcanic activity at Kīlauea and the other Hawaiian volcanoes in order to better understand how, when, and why they erupt. So this is an aerial photograph of the same time period with the lava lake steaming in sort of the center of the photo. And you can see the position of HVO and the Old Jagger Museum, as well as other recognizable landmarks in Hawaii Volcanoes National Park, including the Kīlauea Military Camp, KMC, as well as the Kīlauea Visitor Center. Now, this photograph was taken prior to 2018. And the next photograph, I'll toggle back and forth, is the same aerial view taken after the 2018 Lower East Rift Zone eruption and summit caldera collapse. And you can see some pretty dramatic geologic changes occurred at Kīlauea in a very short time span. Now, the formation of this collapse feature occurred over the course of several months in the summer of 2018. And almost every 24 hours, HVO and nearby communities were rocked by a magnitude 5+ earthquake. These earthquakes permanently damaged the HVO and Jagger Museum buildings, and as such, HVO no longer exists within Hawaii Volcanoes National Park. The buildings were unfortunately condemned, and as of today, they have mostly been deconstructed and removed from Uekehuna Bluff. The bluff is being returned to its original state. Instead, HVO now has temporary home at Hilo Bayfront in town, where we continue to conduct all of our volcano monitoring and research. And so our job as a group is to monitor Hawaiian volcanoes and earthquakes. We assess volcanic and seismic hazards that affect our communities. And we conduct research on volcanic and earthquake activity in order to better understand what the monitoring signals might mean. Finally, we inform the public and safety officials about these volcanic events in order to better protect our communities. Hawaii exists in the middle of the Pacific Plate because it is a unique example globally of intraplate ocean island volcanism. So this is a cartoon map showing every red triangle is a volcano. You see there are many around the edges of the Pacific Ocean, and then Hawaii sits in the middle. So it's formed from a unique set of geologic circumstances. We call it a mantle plume. So deep under the oceanic crust, under the Hawaiian Islands, there is a zone of elevated temperature material in Earth's upper mantle that tends to melt. It forms magma, which rises to the surface and erupts to create each of these Hawaiian islands. This is a nice image showing the ocean bathymetry around the state of Hawaii and the 8 main Hawaiian islands shown here. The Hawaiian Volcano Observatory and our active volcanoes are on the south side of the island chain on the island of Hawaii. And you can see on that island, there are red markings, which show all of the lava flows that have occurred in the last 200 years on this island. And I like this image just because it emphasizes that these islands are massive beneath the ocean waves. So it's not just the volcanoes that appear at the surface, but that this island chain was formed over many millions of years by volcanism that actually creates these massive platforms under the sea as well. HVO monitors the activity of all of the state of Hawaii, but primarily we focus on volcanoes that are currently active, which include Loihi, which is formerly known as Loihi and now Kamaehua Kanaloa Seamount, Kīlauea and Mauna Loa volcanoes, Hualalai, which last erupted in 1801, Mauna Kea and Kohala, which are dormant, and we do monitor activity at Haleakala, whose last recent eruption was only a few thousand years ago, which geologically is still fairly recent. So today we're going to focus on Kīlauea, and Kīlauea, shown here, has a summit caldera, which is circled, and it has 2 arms branching out from that summit caldera. The East Rift Zone, which extends towards the eastern tip of the island, and the Southwest Rift Zone. So our most recent eruption in June 2024 occurred along this Southwest Rift Zone. This is a map of where the eruption occurred in June, just a few months ago. There were 4 eruptive fissures shown by the yellow lines and numbered 1, 2, 3, and 4. This was the first eruption in the Southwest Rift Zone in almost 50 years, And you can see the pink lava flows or the purple lava flows next to those 4 fissures are labeled with the date 1974. So the 2024 eruption occurred in nearly the same place as the last eruption in this area of the volcano. For context, there have been several eruptions in the past few years, but they have all been contained within Halemaumau in Kīlauea at the top of this map. So today we're going to focus on examples of this most recent eruption in the Southwest Rift Zone. The eruption began shortly after midnight on June 3rd, 2024, and we had field crews in the air on a helicopter overflight at dawn that morning to take aerial photographs and do thermal mapping and mark the positions of these fissures on the volcano. We also had geology crews deployed on the ground, making observations from a distance, using some different types of technologies that allow us to measure the length of the fissures, the height of the lava fountains shown here in this aerial photograph, and other things that help us to understand the size, extent, and activity of what was going on that morning. A few hours later, the eruptive activity had waned and effectively ceased, and we had an additional helicopter sample mission that put field crews on the ground near those now inactive vents. So at around 11 a.m., we were able to collect a sample of spatter and tephra. So in these photographs at various zoom magnifications, you can see the dark gray-black material, which is brand new lava that had erupted that morning. The brownish lava flows underneath are much, much older. And so it's very clear to see what the new eruption had produced. And so our field crews walked along the length of those fissures, and I'm holding now in the lab one of the samples that we collected of this spatter and tephra. This is actually me, this photo, collecting this sample. And as soon as I was done with the sampling mission, I drove these samples back down the hill, back to Hilo, where we took them to the University of Hawaii at Hilo, to the geology department, where we work very closely with students and faculty there to conduct all of the research that we're about to share with you now. And at this point, I'm going to hand this new sample over to my colleague, Heather Winslow, and she is going to show you what we do with this sample right after it is collected.
Yes. Awesome. Well, thank you, Kendra. It's a great introduction to our observatory and what we do and the eruption that we're focusing on today. As mentioned, my name is Heather Winslow. I am a new Mendenhall postdoc fellow here at HVO. And my main focus is working on Mauna Loa, but being at the observatory, you're able to work on a lot of different projects and including current eruptions. So this is exciting to have these samples that we got from this eruption recently, and in that same day, we're able to analyze them. So before I show kind of the process from now that we have these rocks in hand, now that we have them in the lab, we're going to go through a lot of steps to extract crystals. And the reason for that is today's focus is that we are a day in the life of a petrologist, so the study of rocks. There are a lot of different ways we can look at rocks and look at different ways of studying an eruption, but today we'll focus on that and focus on the crystal record. And so what we'll go through is how to extract a crystal and get it to a point where we can analyze it. But I want to kind of first get us on the same page of explaining why we care about the crystals that are hosted within these rocks. So to give just a little bit of background here, crystal records inform us of pre-eruptive conditions. So here we have an example of an olivine grain, which is going to be what we focus on a lot today. This is a bright green crystal, and just for reference, mineral and crystal are going to be used pretty interchangeably today. But inside of this crystal, we can actually think about what's going on inside of it that tells us something about the magma chamber. And that's because these internal chemical compositions, their zones, their textures, can inform us about questions like how hot was the magma, or how cool was it, at what temperature was it erupting, how deep was it stored, at what depth did this crystal or this magma come from, was it hosted really deep in the crust and came up quickly and traveled a lot of distance, or was it really shallow and before it erupted. We can also look at textures and chemical compositions that let us know, did the magma interact with other magmas? Did it mix? Did it mix with some of the wall rock? Did it mix with new intruding magma? And then also we can think about something about time here. So how long has the magma been where it's at that certain depth or that pressure, but also how quickly did it come to the surface? So all of this information is really useful and is completely contained within the chemistries and zonation patterns and textures of these crystal records. So they're very useful and give us a window into what's going on underneath the surface. And personally, what I think is very exciting is we're looking at very tiny, tiny microscopic scales that tell us about really big picture things that are happening underneath our feet in these areas. So moving forward from that, we take a sample from the field just like this. We look at the textures, we look at the chemistry, and then it informs us of what's going on so that we can maybe have a picture of what this looks like, of what's going on underneath the volcano. And then one of the exciting parts about geology and about petrology and looking at volcanoes is it's very interdisciplinary. And so we can pair this with other data sets. So thinking about seismicity, so the earthquakes, as well as deformation, which is how the surface changes, or gas data. So we have gas coming out of the ground. All of this combined gives us a really robust idea of what's happening to the volcano before an eruption. And so if we can put all of these data sets together, we can get a much better idea of what's going on. And so today, as noted, we're looking at the June 3rd, 2024 eruption. I just wanted to show some nice images of those hand samples that we're looking at, but also this is an image from that same day in the lab that we are in today processing these samples. So it's very exciting that we get to be in the field that morning, collect a rock, and that same day we're looking at it under a microscope and getting chemical analyses. Oh, and then this is now like thinking, hopefully we'll be able to inform better about what's going on under the surface, specifically at Kīlauea, and we will be focused in the southwest roof zone. Okay, so now if you want to follow me, we're gonna go over to our first step. All righty here. Yeah, let me tilt this just, oh, it's still sharing. Yeah, let's get out of that. Okay. Okay, so let me tilt this down so you can see. Okay, so here I just have a bin here that's empty, and we have a nice piece of paper here to get started. And so before I even start working with a sample, we don't want to have any issues with contamination. So we're going to immediately label everything that we're working on. So today's sample from the June 3rd eruption is labeled KSW for the Kīlauea Southwest Rift Zone 24. And this was sample 4 from that day. So to start, we really need to crush this rock. We need to extract those crystals to get to that record that I was talking about. But to start, we really have to get it out of these rocks. And so we need to break it down. So we're going to pour into here some of our sample. And typically we have quite a bit of sample for each eruption, and this process has to be done quite iteratively and quite often to get enough crystals, but it does depend on the eruption. So some eruptions are more crystal rich and some are not, and that really then dictates how much sample we actually need to process. So many times in science, there's some really high-tech methods that we can use to process things. Sometimes they're also very low-tech, and that's okay because whatever works, works. So in this case, we really are just going to cover this and crush it. So here we have a rock hammer, and we're just going to crush it. We're worried about contamination between other rocks, but not necessarily with the paper. When we go through and process this, it'll be very easy to pull out what is a paper material versus what is the rock, so that's not an issue. So plug your ears or something, or maybe lower the volume if this is too loud, but giving you a heads up now. So if we want to have the camera come over here a little bit. So now we've broken this down, this sample. It was these coarser sizes. It's now been a little bit smaller, but if you look closely, as we dig through, there's actually quite fine material deep down in here. And this is where those crystals are likely coming out of the rock and breaking free. So I'm going to do just a little bit more so we have a bit more material here. All right, so now that we've got a decent amount of material at a lot of different sizes, we're also now going to sieve. And to sieve, This means that we're going to filter through and sort by size distribution so that we can really take out those smaller crystals and get to the right sizes much easier. So for sieving, I am going to wear a mask because a lot of particles can dust up, and so it's good to have some lab safety. There we go. Okay, so now these sieves here are a combination of different sizes. So if you can see this, there's grits at different sizes here. This one in specific is 2 millimeters. So each square in here is about a 2 millimeter size. And it goes down from 2 millimeter. This one is a 1 millimeter size. And then the last one is going to be our finer, less than 0.5 millimeter. And the bottom just catches anything smaller than that in those dust particles. And actually, this is an example of what will be in that final less than 0.5 millimeter size. It's really just dust. Can be used for other things, but specifically for the crystals, this size fraction is a bit too small. Okay. Okay, so now we are just going to pour and transfer our crushed rocks of all different sizes into the sieves. And so this is how it starts. Everything's on the top, and we will shake it and it will sift through all of those different size fractions. Okay, so that is probably processed here. So now we can kind of start to look at the different sizes that we have. And depending on the eruption, sometimes you can already see grains at eye level here. So this first one is just the big pieces are still left that would continue to need to be crushed. This next section is the 1 to 2 millimeter size fraction here. So you can see a little bits of this. If I look at this closely, let's see, I'm trying to see if there's any. I can already see a couple green pieces that are likely that olivine and those crystals here. But then we also have this 0.5 to 1 size fraction, which is going to be right here. And this is where between these two size fractions is typically where we find the most of our crystals for these types of eruptions. And so I would progressively do this until I get quite a bit of material. Here is already a pre-sorted bag of that 1 to 2 millimeter size fraction that we're going to pick through. And so this is a lot more material than what I have already separated, but in general, just honestly not that much compared to what we get in total from each eruption. And all of the samples we really have to sift through to get enough material to analyze. So now I'm going to head over. We're going to go to the next part, which is once we have it at the size that we want, we need to actually pick through and find the crystals themselves. So we're going to go over to some other people and have them pick through these grains. Ooh. Okay, so we are now going over to pick these samples. This is Kama. She has been an intern here with us for the past year and volunteer. She's great. She's been working a lot with cool data sets. And she's going to show us how she picks through these grains, finds the crystals to separate so then we can take it to the next step. So yeah.
Hi everybody, if you guys come over here, I'm gonna share the screen so you guys can have a better view of what's going on. Give me 1 second. Okay, can you guys see what's going on? Oh, there we go. Okay, so this is the 1 to 2 millimeter size that Heather was talking about, and we kind of look at these to see where the olivines are. So right now, this is one mode of how we kind of view to find these olivines. And this is where the magic happens. So I'm going to turn this off and this all the way up. And let's see. There we go. So as you can see, olivine is kind of like a green color, and we kind of look through all of these to see all of these like crystal-like this is an olivine right here, This is an olivine. And then the rest of these over here, like surrounding it, is just glass. So we kind of just like sift through it, pick it. So this is one. And this is like really shiny. I call this gold because it's basically gold. And yeah, so yeah, we kind of just sift through it like that and gather all of the olivine. And once you get all the olivine, you put it in like a separate dish. Bring that over here. And this is all of the gold that I found within just that one section. It may take you like a longer time to look for these because inside all of these samples, you might find like maybe one or two, depending on how much olivine it gives you per eruption. But yeah, this is all of the olivine. And olivine has, it comes in all kinds of different shapes and sizes. And yeah.
Cool. Yep. Awesome. Well, thank you, Kama. So we'll keep the shared screen right now because we're going to show you some other green orientations. But something to note that we're also looking for, don't know which screen to look at. Here we go. Is after we pick these greens, sometimes we also want to orient them, which really means we just want to put them in a certain shape. And so we have a couple examples here of oriented grains. Now, the purpose of this is one of the things we like to do with these grains is get diffusion chronometry. And so if we break that down, what does that mean? Chronometry, thinking about time. So we can get time scales from looking at these, as I mentioned in that kind of initial background. But the way that that works is looking at the distribution of the chemical elements across a grain. And that distribution is connected to time. But sometimes the distribution is different in different directions within that crystal. And then we can get different times. And so we really need to know what direction are we getting at within the crystal. And so this is where we actually have a technique developed by Kendra, as well as another person at HVO, Lil DeSmither. And they have a paper published on this technique where normally you would have to take these olivine grains, put them in another instrument and analyze what direction it's going in. But here we can actually do it by hand. These grains here in Kīlauea are awesome. And so we can actually look at that crystal structure and know what direction it's in. So this is one of the steps that we'll take before putting it into a mount. And so a mount is going to be the next step. We have the picked olivine grains. Whether we orient them or not is fine. It kind of depends on what our goals are. So we can have a combination of those. And then we put it onto a mount making step here. We could probably, oh, perfect, you have that here. So this mount has double-sided sticky tape where we put the individual crystals on there on tape so that they don't blow away or fall out because they're very valuable grains. And here we can continue to orient the shape that we want or just make sure we have the grains that we want exposed at the certain levels. So Kama is showing here on the shared screen kind of what a mount looks like. Depending on the grains, you can get up to like 50 to 80 grains per mount. It really depends on kind of how organized you want to be. But yeah, so we're going to take this mount and fill it with epoxy. There we go. Kama is passing on to our other awesome intern. This is Nami. She is joining us this summer. Perfect. And then stop sharing there. Beautiful. Okay. So here, this is Nami. She has been with us for the summer, and she is going to show us how to make epoxy mounts. And so we'll come around here and get a view. Putting on safety gear because we are now dealing with some chemicals and some materials that you don't really want to get on your bare skin. So we're taking that mount that Kama just had that was already prepped with all the grains stuck onto it, and we're going to mix epoxy, which is a combination of epoxy and a hardener. But it has to be a certain proportion or ratio of those two things. So here is the epoxy resin. And we have, if you can't see, there is a scale inside of here that Nimi is going to use to pour. She's pipetting in a certain amount so that we can really get an accurate proportion and ratio of the epoxy.
It's gonna take a second.
That's okay. Nimi, where were you before this?
I went to school in Washington at Whitman College, and I did my undergraduate thesis research project on the green sand beach over here, which is how I met Kendra. Oh. And then I was able to reach out to Kendra and see if I could come volunteer or find a way to work at HBO. And we managed to get an opportunity funded through the Cooperative Summer Fellowship Program. So now I'm here. I'm super stoked.
Yeah, we're happy to have you.
Yeah, so things that I'm working on right now, other than this is, we're showing you the most recent eruption, but the eruption that I'm working on is the September 23 eruption from last year. And I basically am going through all the same steps that you're seeing today, but I do them all for my eruption. And some really exciting parts of that have been, we've been able to send some of the samples over to California to the probe and have a look at the different zoning patterns, which I know Heather's going to talk a little bit more about here in a second, and get an idea of what different zoning looks like and kind of look at these different stopwatches that the olivine crystals act as.
Yeah. So now Nimi is also getting the hardener aspect of this here. And so we need a smaller proportion of this to mix with the epoxy. And then once this is completed, we have to mix it for about 2 minutes for it to be thoroughly mixed and homogeneous to a material that then we can use to pour into the mount. So it looks like we've got the right proportions, and now we will be mixing.
So the first time I ever did this, I did not mix it enough. And the result you get is it's really hard to see your grains because they're all over the place, the swirls in here. So this actually takes a long time to mix and make sure it's fully incorporated. But you also don't want to go too fast or you'll get lots of little bubbles and then you won't be able to see your grains either. So there's a lot of patience in this job. Slow moving.
Do you need a timer? Or are we?
I think I got it.
She's got it. Perfect.
She's a pro now.
Yes. And so we'll pour this into one of the mounts, and basically this acts to set all those grains that we oriented in place, as Heather mentioned. And then we'll hand it off to Abby, who will be able to polish it down and reveal those cross sections of the grains.
Were these skills of processing these samples something you had done before coming here, or is this a new skill for you?
This is a new skill. I had done some work on the SEM with olivine before, kind of looking at the morphology, so not on the inside of the grains, for my thesis. And then when I came here, I was quickly brought up to speed with all these new skills, because there's always a lot to do and always many, many samples to be processed. So I was lucky to be trained by Bailey and Kama and Kendra.
Yes. So there are many different ways that we can look at crystal records, and this is just one by looking at tephra, and that's when we have these tiny individual grains. And tephra is the explosive deposits that come out from an eruption. Oh, we're moving over. They're the explosive part of an eruption. As I'll get to that in a second. Mimi is now going to pour this in so that it fills the mount puck with the material, so that they can all be together and a cohesive piece that we can look at all of those grains. So now that's been poured, that typically now takes, depending on which epoxy you use, can take several hours to a day or two to fully harden before we're done using it. But we have some pre-prepped ones. So while this one was just poured and is not quite ready, Naomi has a previously prepped one that has been hardened, and now we need to get that out of the puck. And so we're going to show that process. Beautiful execution.
There you go.
So
And
there are all those grains. Yeah.
yeah, right in there. And at this point, we can hand it off to Abby.
Thanks. So our next step, after we have this whole epoxy puck here with our grains, we still have this yellow double-sided tape on it, but to start the polishing process, we have to take that off. Usually it comes off pretty easily. Here it goes. We just peel that right off. And now we have our clean crystals all oriented on there. Toss this tape real quick. Oh, it's coming. There we go. All right. That tape will just go in the trash. And we're off to another room to start our polishing process. So here's our fun polishing room. First thing we're doing with this is it's still pretty sticky, kind of tacky, like a Rice Krispie treat. And so we start on a 240 grit. And so we sit down, we have some water here, we have a glass plate, and we start doing figure eights with the mount to grind down some of the epoxy. So if I do this really quickly, we'll see it starts to turn white a little bit in the water, and that's the epoxy coming off of this mount. And then we rinse it, sonicate it, etc. But already this mount is looking much flatter along the edges here. And we'll actually sometimes do both sides, so it's a nice flat hockey puck. But we go through 4 different grits here by hand. Can take up to several minutes per one. The point of this part is polishing these grains down to about halfway through the crystal, which in the case of doing the orientation method, they're already polished down to halfway. So we're just exposing those nice flat surfaces. Again, doing this whole part by hand can take up to several minutes. And then we take a look at it under the microscope. So I'm going to share screen so you all can just see that. And so here we have 2 different crystals. This is a whole mount of probably 30 plus crystals. But these, we have this one on the left oriented down the A crystal axis, and the one on the right oriented down B. So this is the olivine crystal with some adhering glass. We have these like black vesicles on the sides, and these bright white spots are chrome spinels, which are just minor inclusions in the crystal lattice. You kind of notice this looks kind of dark. We still have these big cracks on the crystal. We don't really see defined edges. So our next step in the polishing process is to take this mount, once it's gone through all of this hand grinding down to a nice flat surface we want, we're going to use an electronic mini met, which does a lot of the work for us. Uses up to 5 pounds of pressure to push this down onto several different grits and really get even the finest nail scratches out of the crystal. So these, we go from 9, 6, and 3 micron diamond suspension polish to then using 1 to all the way to 1/3 of a micron alumina polish to really get the smallest of scratches out, get this a super clean, nice surface. And let me toss that mount onto the microscope real quick. Take a look at it under here. It looks very nice. Naomi did a phenomenal job.
And I'll just interject to say for the audience, what is a micron? It's pretty small. So if you grab a single strand of your human hair right now, that's about 100 microns in diameter. So 1 micron is 1/100th of a human hair.
Yep, so if we look at this crystal here that's relatively nicely oriented, a little broken, we see still have some bigger fractures, which that just happens, it's part of the crystal. But we have these nice edges here that is the crystal face with adhering glass. We still have these vesicles. You can still see those bright white chrome spinels, and in this one over here. But now this is a fully nicely polished mount to which we can image and do quantitative analyses on to see what is this made of? How much magnesium is in it? etc. So I think our now step is we'll take this polished mount, we'd put a carbon coat on it, and we go up to the SEM with Bailey.
That's great. And before we do that really quick, Abby, where are you from? She is an NSF intern.
NSF intern here at HVO for the last 15 months. This one. And I will be returning back to Delaware next week because I'm a graduate student at the University of Delaware, finishing up my PhD on Kīlauea's explosive tephra from about 1,000 years ago. So that's my big research project, but fortunately being here for so long, I've been involved with several eruptions and this near real-time monitoring of what is the chemistry and thinking about those pre-eruptive storage events.
Awesome.
Yep.
Okay, so now we're going to take those mounts. They've been prepped, they've been polished. We now can put them into an instrument to actually get chemical analyses. And we will do that with Bailey up at the lab, and she's going to explain what instruments we're using and how that goes. So hopefully she'll come on shortly. There she is. Okay.
Let's go.
Hi, everyone. I'm Bailey. I'm our physical science technician here at HVO, which kind of means that I just manage our different lab spaces that we have. So like Heather said, or Heather and Abby said, the first thing that we need to do before we use our scanning electron microscope, or SEM, is carbon coat it with our carbon coater over here, which we're not going to do today because it takes a little bit of time to actually get done. But we put that really thin layer of carbon on top in order for those electrons that are going to be shot down through the SEM so that they don't jump all around, so that we can get a nice clear image when we are looking at it on our computer. So this is what it actually looks like when we put them on the mount and when they're carbon coated. You can see here. And we also use some copper tape, which you can see here. And that kind of gives us those electrons a little way to get off of the surface of our sample. So this is all the stuff that we use that we have set out before we can actually put it in the SEM. So we have our little mounts that we actually put the sample on. We have several different mount holders. This one just has several pegs on it so that we can have more than one sample on there at a time. And then these are our little carbon dots, which actually let us stick the grain mount onto these little 1-inch mounts. And then this is our little copper tape that we have here. So first things first, before we start getting into what it actually looks like when it's on the SEM, what is an SEM? So Heather's going to go ahead and share a slide, and we're going to go through it with you guys.
Yes. Okay. Bailey, would you like to pan to just show the SEM from the outside really quick?
Sure. Yeah.
So this is the SEM, which stands for Scanning Electron Microscope. And so now this is what it looks like. There's a lot of kind of detectors on it and pieces to this. And we'll go through that quickly, but just wanted to give you kind of an idea now that we're in the lab, what this looks like from the outside. So I'm going to share my screen and show the PowerPoint again. Okay. So this is, if we were to open that door that we were just looking at, this is the inside of the SEM. And so here we have the sample already mounted, which Bailey has done already for the SEM in this case, and then you close the door. And what this is we can look at surface imaging, so the textures and the morphology of the grains, as well as the chemical analyses. And how this works is we're going to send an electron beam down the instrument, and it interacts with the sample. And then that sample sends back up characteristic X-rays that can be measured. Those characteristic X-rays are how we can get the elemental analyses, because they are characteristic of each element. And so we can get concentrations of that and understand what mineral grain we're looking at, as well as how much of what element is in there. So specifically, olivine is Mg2SiO4. And so we can look at how much magnesium is in there, and we can be like, yes, this is an olivine, but at what scale? Because each crystal kind of has a range of compositions they can fit in. And we need to know at which range in that spectrum this grain is at, because it can be indicative of a lot of those magma chamber characteristics. So once the beam, this is now hitting that surface, there's this kind of activation and interaction volume of the sample that happens. This is a non-destructive technique, so our sample is still intact and it's not making any pits into the grain, as though there are other techniques that do make pits and are destructive. This one is not. And then it sends back up those characteristic X-rays and we can get those chemical analyses. Also, here are just a couple examples of some images we can also get using the secondary electrons. And here we have an olivine that has some crazy things going on because it's clearly not a happy crystal. There aren't nice sides to it. Here we have a plagioclase, which is another mineral. And then here is an example of just a bunch of crystals that have glommed together and grown together. And so just this textural information alone gives us so much insight into what's happening within the magma chamber. And so I think that's it for the slides on this. And we're going to go back to Bailey, and she's going to actually have a sample in the SEM and show us what the grains from the June 3rd eruption look like.
Okay, great. So like Heather said, the secondary electron detection actually just shows us the surface topography, which you can see here. So this is a nice little olivine grain, and we're going to cruise around a little bit just to look at these different ones that we have in here, which we can see that there's some cracks here. There's some bubbles. Things here. Thank you. But this is just kind of showing us on the outside, but we don't actually really know what it's going to really look like until we go into BSE mode, which shows us the deeper regions of this mineral. So if we go into BSE, which it's being a little slow today, so it might take a second. It's on. There we go. There's our nice little olivine crystal that we have in here down a nice A section. So this lighter material that's all around the outside of it is volcanic glass. And then these little bright bits in here are little chrome spinels. So these are, high iron, have a higher atomic weight, so they appear a bit brighter on the screen than some of this other material that has a lower atomic weight to it. And then so we can scroll down. This is a nice example of just an individual crystal of normal zoning. So it has a darker interior here, and then it gets a bit lighter on the outside. You can see this nice gradient here. We're going into a slower scan speed just so we can get a clearer picture. And so that's what that looks like here. And then if we usually go back to faster ones so that we can move around a little bit faster. And to just kind of show you that we think we know what we're mounting when we're doing our nice orientation method, but sometimes it can look like an individual crystal, but it can also just be several olivines that are actually grown together. So this is a good example of one here with all these little buddies it has hanging on the side of it. And this is actually reverse zoning. So it's lighter on the inside and then it's darker around the rim that we can see here. If we go into, again, a slower scan speed, if it will let us, we can see a better example of that. There we go. So this is mostly what a lot of things is what we're looking for when we're up here, but we are really focused on looking for zoning, any sort of like inclusions or any different textures that kind of stand out to us that we're not really used to seeing over here. Let's see. I can show you guys another little example. What these look like. And again, this is some nice budded olivine with glass on the outside, other little crystal inclusions over here. And then we have the same normal zoning that we did when we looked at the first crystal. So darker on the inside and lighter on the outside. And so now we're actually going to do EDS, which we talked a little bit about in the slideshow, which is we're going to hit these grains with those and to basically get those characteristic X-rays so that we can see the different elemental compositions. So first thing that we would normally do is we would come over here, and I was prepping before you guys got on, and you hit start, and it's going to take a nice image and bring it over to this software that we have called Aztec. All right. So now that that's in there and ready to go, we're going to go through and Heather's going to talk a little bit more about this in a minute, but we're going to do a transect or a line profile, which is going to be, we're going to tell it that we want the composition here at the rim into the core. And then we're going to tell it to run. And now it's going to go through and it's going to gather little points of data at, in between these individual steps from this over here at this rim all the way into this core. And while that's running, I think that Heather has a slideshow that she's going to show you what we actually do with that information once we get it.
Yes, thank you, Bailey. Is there a way to see, is it currently collecting data today? Is there a way to see the peaks coming in?
Let's see. Is it on construct line? Okay, let's see.
Yeah, perfect. So if we can get a square view of that, it's just a nice way to look. So as we're getting this line transect, as Bailey said, it's collecting chemical analyses along this line, and we get to see those peaks of those characteristic energies that are being collected. We get to see the peaks of what element that is. So here we can see it's a little fuzzy from our end, but I assume that's a magnesium peak there because we're in olivine. And so this is kind of how we start to look at this data and we're collecting it. The reason we're getting a transect, because you can also do just singular points along to get this chemical data. The transect is helpful for when we're wanting to look at that distribution and change from core to rim, to look back at what we had described earlier, that diffusion chronometry. So if we want to get timescales, we need to understand how the elements and the concentrations are changing from the core to the rim. And so this an analytical technique, typically for this type of thing, we would actually need a higher resolution of data collection using an electron microprobe, but we can get major elements on the SEM and do this quantitatively as well. And so after doing this, I kind of want to give a quick, let's do screen share again. Go. So the reason that we're looking at this zoning is as a crystal is picked up in a magma chamber, it would have a composition at this lower A panel, a composition of one concentration in the magma. It then gets incorporated into another part of the magma chamber or has a recharge of a different magma, and it grows a new rim. And that rim here is that yellow rim here. And this is what we're measuring. We assume that instantaneously that this is a very discrete boundary between that core and the new rim. And then as time progresses, that becomes a bit fuzzy and the elements diffuse. This is where diffusion chronometry comes into play. And so we can actually measure that distribution and relate it to time through some equations to understand how much time has passed to create that gradation of concentration of elements. And so this is how we get timescales. And this is just a couple more examples of these BSE images of what that gradation and zoning can look like in a real sample. So here in this olivine, it has a darker core, just like we saw with the June 23 eruption, and a lighter rim. And then that progression there is what we'd be looking at. So putting it all together, this is a grain. This specifically is a grain from a 2020 Kīlauea eruption in the summit, but this is what we are currently doing with the samples from the June 2024 eruption as well. And this is from Kendra's paper that just was recently published this year. What we are looking at, this is that the black dots here are that distribution of concentration. Here it says FO, this is force-strike content, which is a ratio of the magnesium and iron together. And how much magnesium compared to iron are we looking at? And as we go in that core, there's a lot more magnesium, and then we hit the rim and there's a decrease. This gradation and the shape of that profile is indicative of time. And so this is what we're looking at. And in this case, we're able to get approximately 60 days plus or minus 18 days for timescales for that olivine to be interacted with this new rim and sit there and diffuse and have this concentration gradient become more relaxed. Now, thinking about this, this is very important information, but what does it mean when we put it into scale of what's happening at the volcano? How do we know what's happening? And can we only look at this after an eruption? And so actually we can compare this and use, this is where that interdisciplinary science comes into play. That's really useful to look at other data sets as well. So this is a figure combining a lot of data sets. The bottom here is going to be those diffusion timescales from that eruption. And a lot of them are hosted around that 2-month mark. And then this square here in C is the earthquakes that are happening daily. Above that is the tilt. The tilt is a way that we look at surface deformation, where we have a bunch of instruments out there, and we can see whether or not that instrument is tilting this way or this way. And we have a lot of them at different stations. So let's say our surface is inflating, those tilt measurements would be coming out this way. So we can see the deformation at the surface based on tilt measurements. And then we also have GPS measurements, which is measuring the actual distance of movement. If it's inflating or deflating, how much is it happening? So this is now looking across time from February to December. This is specifically for the December 2020 eruption of Kīlauea within the summit. And we had, after the fact, looking at the olivines, we had a lot of things happening in that 2-month time range. And if we look at, there's an uptick in the earthquakes that are happening, and we have multiple deformation events happening. We're here right before this eruption. We have this big peak in tilt. We have this big inflation happening. And then also the GPS, we had a little bit ramping up at about 2 months prior. And then again, once the eruption is happening. So what's really cool about this is we can put this big picture together. These olivine diffusion timescales that we got from the eruption correlate really well with pre-eruptive unrest. This helps inform us for future eruptions because we don't actually get to see those crystals before they erupt. All we see are these seismic and deformation insights. And we can know now looking back that, oh, sometimes like this eruption had about a 2-month warning prior to it. So it really helps us inform how quickly things can happen. Each eruption is different and it's not always the same every time, but it is helpful to have a record of how it typically behaves in the past. And so this is where it's a really great combination of crystal petrologic data combined with our geophysical data sets. And then also gas can come in here to play as well. But this is kind of how we combine everything. So this is the final image of the June 3rd, 2024 eruption. This is where we collected samples, and everything we worked through today, the samples that Bailey showed us, that was from this eruption. We have some preliminary data on that as well, but since that was so recent, that's still in the works. And so thank you to all of our scientists here that helped out with each part. And thank you all for tuning in. If you have any questions, we're happy to answer any.
Thank you so much, Heather, and everyone who shared this amazing science with us today. This was absolutely fascinating. What a treat to be able to get such detailed insight into, first, what it's like to work, at HVO, taking care of all of the different ways that we can understand what Kīlauea is doing and just about, volcanology in general. This is, for me, an incredible insight into geology in general, because as someone who is very interested in planetary science, we know that, planetary sciences studies really stem from our understanding of geology here on Earth. So could I start with a question on kind of the work that you do when you're first going out to collect the samples? We saw a picture of Kendra out, which was just amazing. And there was this large pillow of, I think maybe it was pahoehoe beside her, which looked like it was maybe 1 or 2 feet tall. I can't tell. How often are you on call to be able to go out and respond to an eruption? Is there like a cycle of who's on call or not? Or is it just kind of, there are specific scientists who are always on call in case an eruption occurs?
Yeah, that's a great question. And I'm happy to give some of my insight. I've only been here since January, and also if anyone else wants to jump in, but I can give kind of my first thought. That's a really great question because it is confusing. Like, what is going on? How do we know who's going where? So one thing to note is that it's a really big team effort. We have a lot of people and a lot of team and communication happening prior to an eruption. Ideally, before an eruption, there will be some type of uptick in unrest, whether that's seismic activity, gas, or deformation. So ideally, as that's running up, we are starting to have more meetings and more discussions about who's going where and what happens if an eruption happens. Eventually, we get to a certain place where it's at such a heightened activity, we change the alert level. And that once it gets to there, we are more on official shifts that are rotating so that we don't tire out our colleagues. And so that you're hopefully only on an 8-hour shift. If an eruption happens during that time, you're going to be the one that goes out immediately. And then everyone else will come in to support and relieve you as their shift comes around. So that's kind of what happens, and who dictates those shifts is an internal conversation of who's available and what's going on. But it really is just like a team conversation of what's going and what resources do we have at that time. And so, yeah, there's that. Any other, and frequently when these eruptions are happening, a lot of our team who maybe aren't going out and actually sampling or going to do the eruption response are up late into the night watching the earthquakes come in, watching the deformation, and sending us alerts. So that's why I said it's a really big team aspect. Is there's the people going out, and that's a whole team, but there's also a behind the scenes team that's looking at the data coming in and informing us, and also for our safety to be like, if you're out in the field, okay, it's ramping up again, be aware, this is where it's happening. So yeah, hopefully that answers that question.
Fantastic. Yes, it does. And I did just drop a link in the chat to the Hawaiian Volcano Observatory, which I noticed I just misspelled observatory there. Apologies. Okay. In the chat. Hawaiian Volcano Observatory webpage, where we can actually see that the alert level right now for Kīlauea is yellow. So that's just perfect from what you were just saying. We can see that that's in action. Now we have several questions in the chat. Let me go back first to Vani. Vani asks, what software programs are used to analyze each item? Because it was amazing to see through the scanning electron microscope into actually seeing what's inside of those rocks that you were, breaking down earlier. Absolutely fascinating. So yes, what software programs do you use?
Yeah, so the microscope itself is the SEM there's a lot of different brands, but there's a JOL, which is JEOL, or Hitachi. There's a lot of different instruments that are just the instrument themselves. But then the software we use to actually analyze, in this case, is out of Oxford. It's the Aztec program. I'm not sure I have much more information than that on it in there, but that's typically, I've been to quite a few labs that have used this technique, and they're all using Aztec. So I'm not sure. There are probably other ones, but that's typically what I'm familiar with.
Thank you. Thank you. So Garima asks, can you share your thoughts on extrapolating your research findings to the understanding of other volcanoes in our solar system, such as Jupiter's moon Io, which we know is the most volcanic body in our solar system, which is covered in hundreds of volcanoes. I think there's at least 100 going off at any given time.
Yes, and I'm going to have Kendra actually jump in and answer some of these questions as well to give you guys some different perspective.
Yeah, so fantastic point about volcanoes in our solar system. Plug, has research interests in pursuing a graduate degree in planetary geoscience, and exactly this question, studying volcanoes in our solar system. So she's very excited that that question was asked. Did you know that the U.S. Geological Survey has an astrogeology center? So it's located in Flagstaff, Arizona, and our USGS colleagues actually tackle questions like this, where they combine sort of the astronomy field and the volcanology field together and tackle those issues. So we at HVO do not do things outside of the state of Hawaii, let alone the solar system. But if you're interested in more information, please look up the astrogeology program. And then someday Kama will be the expert on such a topic.
Wonderful. So if we could maybe ask Kama really quickly to maybe share her insights on this question, since this is part of what you are studying. How can you, what is your connection and how do you connect your studies here at Hawaiian Volcano Observatory with your interest in planetary science on a larger scale?
Yeah, that's a great question. So I am a double major here at UH Hilo. I'm still an undergrad. So I have spent some time getting my astronomy degree. I'm almost done with it. So I had an interest in taking more geology classes because I took a astrogeology class last year. And I kind of didn't understand the material because there's a lot of geology like jargon that was going on. So I was just like, maybe I want to learn more about this. So I took intro classes and then I really liked it. So I kind of like changed my majors into astronomy and physics. And then now I am astronomy and geology. So I really wanted to study like volcanoes in Hawaii. It's because I dance a lot of hula and it's part of my culture to go visit, hula pele and just kind of combining that science and integrating the culture in it, just to try and understand and connect better to kind of combine Hawaiian culture and science. And that was one of the main goals in PIPES, the internship that I was in. So the PIPES stands for Pacific Internships Programs for Exploring Science. And they did a really good job with that. And one of our waka'is, or like our field trips, our journeys that we went to was by the volcano, Kīlauea, and also Mauna Loa. We did protocol, and we had a fun little workshop on how to make lei and how to kind of insert ourselves into a place of sacredness and asking for permission and all that kind of stuff. So I find that going to Kīlauea kind of really connected me more to my culture and finding more intimacy with the akua, the gods and stuff. So as I was searching for something to do with both my astronomy and geology degree, I kind of like combined that and both the astronomy and geology aspects. And I was like, maybe I can study volcanoes on like the moon, on Mars, and thankfully Jupiter's moon, Io. So I know that that's one of my goals in life, and probably hi baby, probably a research that I can do in my my graduate degrees. So yeah, I hope that answers your question. I feel like more of the research that's going to come, if I do get the chance, I will be happy to share it with everybody. And yeah, hope that answers your question.
Yes, thank you. Thank you, Kama. Thank you so much. It definitely does. And congratulations. Congratulations.
Thank you.
Okay, so for everyone, we have another question. Is there any science connecting the moon phase and a volcanic eruption?
So there are some scientists globally who are researching the impact of tides and the forces related to tides and moon cycles, and how they exert pressure or don't on a volcanic system and maybe influence an eruption. That is not my kuleana, and that's more in the geophysics sphere, but it is a hot topic that people are digging into. But I leave that to the experts.
Okay, wonderful. That was a great question. I didn't even know that there was a possibility of a connection there. So thank you for that question, Joshua. Now, you were talking about well, you mentioned earlier on a green sand beach. This is on the Big Island of Hawaii down in South Point. And so the green and the sand is the olivine. Now, olivine has been found, in many places, of course, on our planet, but also on Mars. So are there different ways that olivine can form?
Olivine is arguably the most common mineral in our solar system. So not just on planet Earth, where it certainly dominates in Earth's mantle and in Earth's volcanic systems, but certainly celestial bodies and other things. You know, we have meteorites called pallasites that are just riddled with olivine from other places in our solar system. And so in a lot of ways, olivine formation and the histories it records are related to the birth and death of planets and their evolution through volcanoes. You can also form phayolitic or iron-rich olivine in hydrothermal systems. So there are a number of different other ways that olivine might grow, but it's going to have a very different chemical fingerprint compared to something you might find in a meteorite or in a volcano.
And I would like to add there, so Mars has a lot of like volcanic features on it, and they're really large because Mars is a bit more unique or different from Earth in that there aren't necessarily the same like plate tectonics happening or plate tectonics at all. And so we aren't getting that moving, just like the Hawaiian chain is moving away from a hot spot. So you're getting kind of progressive islands. If they're not moving, it just keeps building upon the same thing. So we have some really large volcanoes on Mars because it's erupting, there's a volcano there, but it's not moving away from anything. And so also olivine is probably coming out of those types of eruptions as well.
Wonderful, wonderful. Thank you so much. I would just like to say to those of you joining us who are in the chat, if you have any other questions, please pop those in the chat now before we wrap up with this amazing team. And while we're waiting for any more questions, I just like to, yes, it's great to see all of you. I just like to say that it's great to hear about the internships, the programs that allow some of you to visit and learn and work at HVO with these amazing scientists here. Now, we heard that you're all from several different states. Does the internships at USGS, do you have to be in the United States to apply for those internships? Can you be at an international school and apply?
There are several different ways that student internships can occur with HVO. There are some that are federally funded, and those are limited to US citizens, the way that most federal hiring positions are. But then there are many opportunities where the funding comes from another source, like the University of Hawaii at Hilo through the PIPES program, or Abby's funding, which comes from the National Science Foundation. HVO does have a very long history that predates me by a long shot of folks bringing funding from a home institution anywhere on the planet and being in residence at HVO. And so that is something, you know, that it has been supported for a very long time.
Wonderful. So we have another question, and I don't want to mispronounce the name, so I will not say it. But the question is, I really wanted to ask if HVO, Hawaiian Volcano Observatory, has any opportunities for online internships or a way to virtually, kind of participate in learning in that way.
It's a great question. And I'll say that if, there's one thing that COVID taught everyone, right, is that we are adaptable to be able to have virtual environments. And so although it hasn't been a big component of HVO's program in the past, I don't see why it couldn't become part of our future. And I would say that the key to any kind of internship or finding your way to work with someone at HVO is to make connections, find a good match with a mentor who has time and interest and mutual, research goals, and then move on from there. And so I would say that if you have any other specific questions about opportunities and how to develop them, we have an email account, Ask HVO, so lowercase ask, capital HVO, at usgs.gov. I can put it in the chat in just a moment. And you can send any of your inquiries there and someone will respond directly to you. So this is a perfect kind of question for that person who monitors that email account.
Wonderful. Oh, that'd be so welcome. Thank you for putting that in the chat. Okay. Thank you. There it is. Oh, let me just copy and put it in for everyone. Okay. So now we have another questions from Annalise. And Annalise asked, is there potential for citizen scientist participation via Zooniverse, kind of like Zooniverse on SciStarter, for example?
I am unfamiliar with the words universe and SciStarter. Anybody? Anybody? I'm not sure I can answer that question. I've never heard of those things.
So SciStarter is just I'll drop it in the chat. It's a place where a lot of citizen scientists projects are. And Zooniverse was one of the first ones that allows everyday people to contribute to like galaxy identification, among other things. And so there are many projects there, from identifying different types of fish to other geological projects as well there too. So I don't know if I've seen anything on volcanology and SciStarter yet for citizen science participation, but do you know of any that we could maybe share?
Which I don't know any off the top of my head, petrology related, and this is likely only limited to those in Hawaii. But we have a thing for all of the earthquakes and the different seismic network, that if you are at your house and you feel an earthquake, you can go on the HVO website and it will be like, oh, there was just a 3.1 earthquake in Pahala. Did you feel it? And if you click that, did you feel it? You get to fill out a little form of where are you? Were you on the first floor, the second floor of your house? Were you sitting down? Were you standing up? Did the walls shake? Did they not shake? And those sorts of things. That is a good citizen science thing here that monitors, oh, where did people feel it? How many people felt it? Because some of them, only 3 people felt it, or at least only 3 people reported feeling it. Other times it's like 30 plus people. Everyone was like, oh, I gotta go fill out that form. That was a big one. So things like that are important for the earthquakes and the different monitoring system for the public here. But I don't know of any petrology related ones that are out there.
And it may be that you all are the first to create those petrology centered citizen science projects. Thank you so much for that. We'll ask, well, actually, let me go back up to Annalise. Elise says she could be useful for identifying lots of crystals if you need help. I believe Annalise is working on her PhD in either astronomy or astrophysics. She's one of our frequent participants from South Africa. So yes, we'll connect you with her in case you're interested. Okay, now we'll ask, when will the next eruption at Kīlauea occur?
Well, I will say that there has been some periodic seismic unrest in the upper east drift zone of Kīlauea. And as of recently, I think yesterday or the day before, an information statement went out about like the middle east drift zone of some tilts and ground deformation occurring very slowly with time, but it does signal to the public that something is changing a little bit. There are no signs of imminent eruption, but I do hope that Pele makes an appearance before I leave next week.
We will say that that is the core mission of HVO and its many interdisciplinary scientists, is to better be able to answer that exact question. As of today, there's no, surefire way to forecast or predict any kind of volcanic activity globally, let alone here. And so it's something we strive for, but not something we can deliver.
Can I add something real quick? So in Hawaiian mythology and history, there's a lot of like chants and dances that we do where we talk about certain eruptions that happen within the time period of the building of the volcanoes in the Hawaiian Islands. And each chant kind of matches up to like each eruption that happened like thousands of years ago, 100 years ago. So we use oral tradition to kind of pass on that knowledge, and a lot of that knowledge is shared yet, but I'm gonna try and make an effort to try and do that for HVO. So yeah, just wanted to share that.
Kamer makes a good point that the best way to think about the future is by learning from the past.
Absolutely brilliant point. Thank you. Thank you so much. Okay, and so thank you for all of the wonderful questions. And maybe to wrap up, I'm going to share my screen, and I would appreciate it if you could, oops, not that screen. share with us what we're seeing right now. Now, this is a live view of Halemaumau crater in Hawaii Volcano National Park. This is Kīlauea volcano, and we can see lots of activity. What's going on?
Yeah, so we have a live streaming webcam that's up 24/7 if you ever feel like checking in with Kīlauea to see what's going on. And this view, which is live today right now, it's probably a little bit misty or rainy up in the park. You can see a bit of cloud in the upper left, but all the signatures that you're seeing on the floor, the black floor of the caldera there, that is active steaming, volcanic gases, but mostly water vapor. And it's because the summit caldera is still quite hot from all of the recent eruptions we've had. So the dark black material is fresh lava surfacing, likely related to the September 2023 eruption or another recent eruption. And then the brown and white that you see mantling on top of the black, those are secondary mineral deposits, things like gypsum or sulfur or other kinds of minerals that form in these hot volcanic environments.
Fantastic. What an amazingly interesting, engaging, fun session. We had quite a few compliments here that this was a fantastic session, that we want more of these. So I look forward to being able to connect with you all again to share more amazing science from the Hawaiian Volcano Observatory. And I will leave the last words with Kendra and your team.
Just want to say big mahalo for coming and hope you learned a lot.